Hello all, we are starting chapter 2 now. In chapter 2, we're getting into atoms, molecules, and ions. The first topic we're going to cover in 2A is identifying the parts of an atom. Now, importantly, before we go into those parts of the atom, we are going to cover some crucial historical moments leading up to the discovery of those parts of the atom. One important historical factor in chemistry is Dalton's atomic theory around 1808. So it's pretty remarkable that Dalton came up with this theory. So remember, theories are not necessarily true. It's just what he theorized to be true based on the evidence that he had. So let's go through the main 4 points of his theory. The first point in his theory is that elements are composed of extremely small particles called atoms. The second point here, all atoms of a given element, be it carbon, oxygen, hydrogen, etc., are completely identical, having the same size, mass, and chemical properties. The atoms of one element, therefore, are different from the atoms of all the other elements. This one is going to be important because we come back and prove why part of this point of Dalton's atomic theory happens to be incorrect. The part that's going to end up being incorrect is based on this notion that all atoms of a given element have the same exact mass. So again, we'll come back to this. His point number 3, we did see in chapter 1 on compounds, where compounds are composed of atoms of more than one element. For example, here, ozone is 3 oxygen atoms together. So 3 oxygen atoms bonded together. This is not an example of a compound, right? Because it has to contain atoms of more than just one kind of element. What ozone is an example of is that it is a molecule. So for something to be a molecule, it can be composed of all the same element. We'll see molecules more in 2B. So in chapter 2B, we'll come back to molecules. We'll go into this part of his theory for point number 3 in just a slide or 2 from now, where the ratio of the numbers of specific atoms of any 2 of the elements present is either an integer or a simple fraction. So we'll go into this one more. The 4th point of Dalton's atomic theory is that for a chemical reaction that involves only the separation, combination, or rearrangement of atoms, very importantly, it does not result in their creation nor destruction. This ends up being a pretty important point in chemistry and in physics as well, that relates to the law of conservation of mass, where matter can neither be created nor destroyed. It can be broken down, it can be put back together, but we can't create nor destroy something just out of nowhere. So I mentioned we'd come back to this point more on the ratio of the numbers of atoms of any 2 of the elements present is either an integer or a simple fraction. For example, carbon monoxide is an example of a compound. It contains carbon and oxygen, so 2 different elements. The ratio of these 2 elements, carbon and oxygen, is a ratio of 1 to 1. This is an example of an integer ratio, right? 1 is an integer and 1 is also an integer. Another example of a compound is carbon dioxide now. So it contains 2 different elements, carbon and oxygen. The ratio of those 2 elements now, though, is not 1 to 1, but it's still an integer ratio, so 1 to 2. An example of what is not a simple fraction or an integer ratio would be something like there are 1.37 silicon atoms to 1.54 carbon atoms or something like that. So that's not an example of an integer or a simple fraction. More on this point for Dalton's atomic theory, so this law of conservation of mass that was mentioned. To see this play out, to see an example of this, if we have 16 atoms of X, and 8 of Y. Let's say they come together to form a compound of X and Y. So they contain 2 different elements. So that's definitely a compound. When these come together, they're in the ratio of 2X to 1Y. And importantly here in this reaction, we still retain every one of the 8 Y atoms. So that's present here. And also we still retain all 16 of these X atoms. So those show up here. What we're seeing is no X is lost, no X is just magically appearing here on this side of the reaction. And same for Y. So all the Y that's present here is also present on this side of the reaction. We'll cover reactions more, but to give you a preview, anything on the left-hand side here, these are called the reactants. Then we have this reaction arrow here, and then things on the right-hand side are called the products. Another important part of chemistry, speaking historically, is the experiments that J.J. Thomson did with the cathode ray tube. We'll see in just a few slides from now that electrons are one of the subatomic particles of an atom, and they are negatively charged. What Thomson used were these cathode rays in his experiments, which were later classified as electrons. What Thomson did is he found that these cathode rays had some mass to them and they were negatively charged. What Thomson didn't do is he wasn't able to nail down the exact mass of one individual particle, but he did find that these particles all together were negatively charged. So the takeaway from Thomson is he was able to show that electrons are charged particles, specifically they're negatively charged. And he wasn't able to nail down the exact mass, but what he was able to do is calculate this charge to mass ratio. So his takeaways here, he knew they were negatively charged, but he didn't know the individual mass. He just knew this charge to mass ratio of negative 1.76 times 10 to the 8th. This is coulombs per gram. We'll see this again in a few slides from now, so we'll come back to this. The way that Thomson was able to understand and recognize that electrons are negatively charged is through this design, so his cathode ray tube experiment. What he did is he took magnets which are polarized, so we'll see polarized again a little bit later on in the semester. What polarized means here for a magnet, and also you're used to hearing about the north and south poles of the Earth. So because magnets are polarized, it means here they contain areas of both positive and negative charge. So when Thomson placed this magnet in the way of these cathode rays, specifically when the negative end of the magnet was placed in the way of these rays, which we know turned out to be electrons, the electrons were repelled in the presence of the negative end of the polarized magnet. Why would they be repelled? Well, we remember that like charges repel one another, so negative end of the magnet and negatively charged electrons are going to repel one another. This is how he was able to describe that electrons are particles that are negatively charged specifically. Now, similarly here, if you put the positive end of this polarized magnet in the way of these cathode ray tubes, where the cathode rays are electrons, then what do you think happened with the positive end of the magnet and the electrons? Well, here the electrons were attracted to the magnet because opposite charges attract. So the positive end of the magnet did attract those electrons due to the opposite charges. So opposites attract and like charges will repel one another. Now, what Millikan was able to do, based on the discovery of Thomson, remember Thomson was able to get a charge to mass ratio, but he wasn't able to nail down the specific mass or the specific charge. Thomson just found out that electrons have a negative charge to them. Millikan, however, his main takeaway is he was able to actually determine the specific charge of an electron. Then, given the charge of an electron and given what Thomson did, he was able to then get, importantly, very importantly, the mass of an individual electron. So again, he found the charge of each individual particle, then he put that together with what Thomson had done to get this big discovery of the actual charge and the mass of an electron. This capital C here is a coulomb. It's the SI unit, it's the standard unit for electrical charge. Then we've seen grams before, so that's mass. You might notice the exponent here of how light an electron is in grams. It's very, very, very small mass. Similarly, the charge is very small as well. Now, another important point before we get into those subatomic particles, we've talked a lot about electrons so far. Now, another concept here is the different types of radioactivity. So there's alpha radiation, beta radiation, and gamma radiation. Using this idea again of like charges repelling one another and opposite charges attracting one another, there were experiments done using a radioactive substance that did emit alpha, gamma, and beta radiation. With this positively charged plate here, along with this negatively charged plate here, and then the direction that these different types of radiation went when they were passed over or passed between these plates, we could then tell that alpha radiation is positively charged. Then on the other hand, beta radiation went towards the positive plate. So from that, we could tell that beta radiation is negatively charged. Lastly, when gamma radiation passed through these two plates that have a negative and positive charge, it was not impacted by those plates, so gamma radiation is neutral. It has no charge. You'll see how radiation becomes important as we get into the next experiments. Another important historical moment here is Thomson's model of the atom. Ultimately, it's important to note this model is incorrect, but it gave us a very good idea of what could be happening in the atom. Now, again, this is the incorrect model of the atom, but let's go through it. What the scientists knew at this point is that electrons do exist, so they're negatively charged particles. Given the stability of these electrons, it was then assumed that there is this positively charged sphere that surrounds these negatively charged electrons. So, why is it called a plum pudding model of the atom? Well, you can imagine that this portion, this positively charged sphere, is the main part of this plum pudding. What is this main part? I couldn't really say. I'm assuming it's some sort of breading. Then these negatively charged electrons were the sort of raisins in this plum pudding. So Thomson's model of the atom, sometimes referred to, pretty commonly referred to as the plum pudding model of the atom. Now, using radiation, so what we just talked about, Rutherford actually designed this experiment. We remember that alpha particles are positively charged, and what Rutherford found is that when positively charged alpha particles are passed through this pure gold foil, then some of the positively charged alpha particles were able to pass straight through the gold foil, which we know now is composed of these gold atoms. So some positively charged alpha radiation was able to pass straight through the foil. However, some of that alpha radiation was deflected back at very sharp angles. How could that be? Why would positively charged radiation like that come back and be deflected so intensely? Well, that made Rutherford doubt this plum pudding model of just these electrons dispersed throughout in a positively charged sphere. Because if that were the case, then the alpha radiation could fairly easily just pass straight through the gold foil that's composed of these atoms, no matter what. But what turns out to be true is this positively charged alpha radiation is encountering something and then being deflected back. That something, if the alpha radiation itself is positively charged, it probably means that something is also positively charged. This was a huge discovery now because that positively charged something is what we know now as the nucleus of the atom. So now our new idea of what this atom might look like is we can still have these electrons that are dispersed throughout, but what we now are thinking, or what Rutherford is thinking, is that there's this positively charged nucleus that's concentrated in the middle of the atom. What this positively charged nucleus, all we know right now is that that area is positively charged. So at this point, Rutherford is able to say the charge of an electron is negative, and then what's in the middle is something that's positively charged, which is the proton. What else did the scientists know at this point? The mass of a proton that's positively charged is much, much, much greater than the mass of an electron that's negatively charged. Another fun way to think about this is if the atom is the Houston Astrodome, then the nucleus is just one marble at the 50-yard line. Looks like there's baseball set up in this image, but you could imagine this could also be set up like a football field. And so the nucleus would literally be one marble in the entire Houston Astrodome, where the little marble is the nucleus, and then the entire atom is the Astrodome. This analogy is based on the fact that the atomic radius they found out to be about 100 picometers, whereas the radius of just the nucleus, or called the nuclear radius, but the radius of just the nucleus is only 5 times 10 to the negative third picometers. What's a picometer, you might ask? Well, you might recognize this from chapter 1, where if we're going to use this table here that we're familiar with, 1 picometer is equal to 10 to the negative 12th meters. So it's very, very small length. So at this point with Rutherford, we have negatively charged electrons and some positively charged protons. There's one more subatomic particle that hasn't been initiated yet in this discovery process. That is not until Chadwick came along. What Chadwick did is he recognized that hydrogen contains 1 proton and helium contains 2 protons. Because electrons are so light, their mass is essentially negligible. So if we're comparing the mass of hydrogen to helium and only protons are present in the nucleus, then we should have a mass ratio of just 1 to 2, because protons are the only items that are adding mass to the nucleus of those atoms. However, what Chadwick saw is that the ratio was not just 1 to 2, instead it was 1 to 4, meaning that something else must be present in the atom that is adding mass. And based on the electron and proton that were already discovered at this point, the electron is negatively charged, the proton is positively charged, and there is no other charge at play. However, there is something adding mass to the atom. It turns out that Chadwick is the one that contributed this idea of a neutral neutron that's present in the nucleus of an atom. So neutrons have no charge, they're neutral, and something else important to note is that the mass of a neutron is about the same as the mass of a proton. And remember that the mass of a neutron and the mass of the proton then are much, much greater than the mass of an electron. Okay, so these are the important historical discoveries, and now we'll move on to some properties of these subatomic particles that were discovered. What's important to know here, electrons, represented usually as that lowercase e with the negative sign, they are negatively charged. Protons, represented by that lowercase p with the plus sign, they're positively charged. Neutrons, you might see like this sometimes, or just a lowercase n. Same with the proton. Neutrons are neutral, they have no charge. What else is important here? The mass of an electron is so much lighter than the mass of protons and neutrons. Moreover, the mass of a proton is approximately equal to the mass of a neutron, which again is much, much greater than the mass of an electron, roughly 1,800 to 2,000 times greater in mass compared to the electron. This becomes important because as we talk about the atomic mass, so the mass of an atom, we count the electron's mass as negligible. They're so light compared to protons and neutrons that we don't really think about the mass of electrons here moving forward. This is another table that might be helpful to have to refer back to. The points here now, so the protons and neutrons are within the nucleus and the electrons are sort of orbiting around the nucleus. The mass of an electron now is so much smaller than the mass of protons and neutrons. Here's another way to see that mass difference. Now, another very important part here is when we start to think about the atomic mass and in these atomic mass units. Protons' atomic mass unit is just 1. Neutrons' atomic mass unit is also just 1. Wait, I thought that the protons and neutrons weighed about 1.67262 times 10 to the negative 24th. Well, they do in grams. These numbers are highly inconvenient to work with. So while we know the exact mass in grams of protons and neutrons, we don't usually talk about the mass in the units of grams. To make things simpler now, the mass of a proton we call 1 AMU, or 1 atomic mass unit. Same with the neutron, we say neutrons weigh 1 atomic mass unit. Okay, so for masses, know that a proton is 1 atomic mass unit, We're not talking about grams here. We're talking about these more convenient units of atomic mass units, or AMU. Neutrons also weigh 1 atomic mass unit. Electrons, again, essentially negligible. They're such a small weight, atomic mass unit-wise and gram-wise. We essentially call the electron mass negligible. This is how we view the atom now, mostly. Notice it's not the plum pudding model. So how we view it today is, again, we have this nucleus that contains the protons and neutrons. Protons, positively charged, neutrons, neutral, while these negatively charged electrons sort of orbit around the nucleus. Why again did we simplify the mass units? Well, now we could say that the nucleus weighs, so there's 1, 2, 3 neutrons. That's 3 atomic mass units. There's also 1, 2, 3 protons as far as we can see. So that's another 3 atomic mass units. What becomes really nice now to work with is that we call this whole atom, just based on the masses of the neutrons and protons, 6 atomic mass units. We're not working in grams anymore. We get to work in this convenient atomic mass unit. Okay, so that was that topic. The historical components leading up to this discovery are important to know. Next, we're going to go into reading a periodic table entry. So you'll see a lot of periodic tables. Each box will look different. Each element representation might look different depending on what periodic table you're looking at. Not all periodic tables will show this electrons per shell, but what you will see is the element symbol, the atomic number, and the atomic weight. So recognize in this version of the periodic table, we have the atomic number here, then we have the symbol, then we have the mass here, the mass or the atomic weight. Now you can also see elements represented like this on their periodic table. And just in general, not necessarily on a periodic table, but recognize that if you see an element that's listed like this is still the element symbol, so it'll be a 1 or 2 letter symbol to identify the type of atom. On the upper left here is always going to be the mass number. Where was the mass number here? Well, the atomic weight is the same thing as the mass number. So mass number was here, but then in this depiction, it's up here on the upper left. Also, very importantly, the atomic number is here. In this version, the atomic number was listed up here. Now recognize in this representation of elements, it's down here in the lower left. So as we talked about for the mass number, the mass of the electrons is essentially negligible, right? Because the mass of electrons is so much lighter than the mass of protons and neutrons. So what is this mass number then? It's going to be just the number of protons and the number of neutrons added together. And because 1 proton weighs 1 atomic mass unit and 1 neutron weighs 1 atomic mass unit. We'll do some examples of looking more at this, but remember that the mass number is going to be the mass in atomic mass units of protons and neutrons. But even easier to understand, the mass number then is also the number of protons plus then the number of neutrons. Remember, because 1 proton is the same as 1 atomic mass unit, 1 neutron is the same as 1 atomic mass unit. What's happening down here then? This atomic number you'll see represented as this symbol Z. The atomic number is always the number of protons in the nucleus. Notice that so far electrons are not mentioned here in the mass number or the atomic number. Very important concept here. The atomic number Z, the number of protons, that is the only thing that determines the identity of the element, other than the element symbol, of course. The number of protons will be the same for elements. For one specific element, the number of protons will always be the same. If the number of protons changes, we have an entirely different element. So if the atomic number is always the number of protons and the mass number is the number of protons plus neutrons, then from the information given here, we can easily figure out the number of neutrons. To do this, we would find the atomic number, that's the number of protons. Then we subtract the number of protons from the mass number. That will give us our number of neutrons. Again, we haven't talked about the number of electrons yet, but we will. Here's just another comparison of these different representations. Remember, if you see something like this, the mass number is here on the upper left, the atomic number is here on the lower left. As a heads up, you might not see the atomic number listed each time. Why is that? Well, we can tell what the element is based on the symbol. So what I mean is that you might see it listed like this. How do we know the atomic number then if it isn't listed? Well, we use this element symbol to find out what element it is. Then we go to the periodic table, and then we find its atomic number. So this number is not always listed, so be careful with that too. But we can find that number just based on the element symbol. Then we go to the periodic table and we find the atomic number. That's the number of protons. So that's here textually what I just mentioned. Something else to be aware of here is that the mass number can also be referred to as the atomic mass or the atomic weight. Okay, so mass number, atomic weight, atomic mass, this is all the same meaning of the number of protons plus the number of neutrons. The atomic number isn't really called anything else, but you might hear it referred to as Z. So atomic number, Z, the number of protons. Yet another thing to be aware of is we've talked about these atomic mass units and how convenient it is that one proton is one atomic mass unit. One neutron is also one atomic mass unit. You might see it shorthanded as just this lowercase u, so know that that is the same thing. There is another unit here that is also the same thing, so you could also see this as Daltons or just dA. These are all the same. So for example, one proton is still equal to one Dalton now. As a heads up, we will also see atomic mass units be equivalent to grams per mole, so we will come back to this a lot throughout the semester. To remember the scope of where we are, this is the same flowchart from chapter 1. Remember that in the category of matter, within substances, we can have compounds and elements. So here we've been talking all about elements. Here's another slide you've seen before from chapter 1. So just another reminder on the definition of an element. It's a pure substance. Also importantly, it cannot be separated into simpler substances by chemical means. As we know now, each element is composed of an atom with protons and neutrons in its nucleus. I should say each element is composed of atoms, so plural. Then around that nucleus, we have these orbiting electrons. So all these atoms make up each element. And as you might imagine now, it'd be pretty difficult to imagine that a proton and a neutron can be separated just by pretty simple chemical means. This actually gets into the idea of the atomic bomb, where we're trying to tinker with these different subatomic particles. Okay, the next important topic here is isotopes. Now, I mentioned that the atomic number is the number of protons. It's also the identity of the element. The number of protons tells us what the element is. The number of protons will never change for a specific element. Again, if we're working with a different number of protons all of a sudden, we have a different element entirely. But what can change for an element, let's say if the number of protons is consistent, what can change is the number of neutrons that are present in the nucleus. So for isotopes, it's the same element, meaning it's the same number of protons, right? That's how we should read that. Same element, same number of protons. So same element with different number of neutrons now. Think about this question. As isotopes have different numbers of neutrons, how will this impact the mass number and the atomic number? So hopefully you recognize that the atomic number will not change, right? The atomic number for an element will not change if it's the same element. The number of protons does not change, therefore the atomic number does not change. What is going to change then, if we're adding neutrons to the nucleus or we're taking neutrons away, this will impact the mass number, because the mass number, again, is the number of protons plus the number of neutrons. So the number of neutrons will be different for different isotopes, therefore the mass number will also change if we're dealing with an isotope. Isotopes are actually really common. Most elements have 2 or more isotopes that exist. A big takeaway here, elements that are isotopes have the same atomic number, same number of protons, but different mass numbers, which I should mention can be represented by an uppercase A. So mass number, atomic weight, atomic mass, or uppercase A, that will change when we have isotopes because we're changing the number of neutrons present in the nucleus. Let's look at an example here visually. Now we're seeing elements listed like this. So we recognize that the upper left is the mass number. Then the lower left here, if it's present, is going to be the atomic number. If that were not present, we could still tell what this is. For example, 1H. We don't have to see if the atomic number is 1 to know that hydrogen has an atomic number of 1. Why don't we need to be told that explicitly? Well, we can go to the periodic table, find the element symbol for hydrogen, then locate its atomic number. So this one could be represented by 2H and 3H and so on. But here we are actually given the atomic number each time, even though we could figure it out. So what's happening here is that the atomic number is not changing. We're still dealing with hydrogen each time with an atomic number of 1, meaning we have 1 proton present. Protons are here in red, so you recognize the number of protons is not changing. Number of protons does not change. What is changing is the number of neutrons that is present alongside that proton in the nucleus. These are different isotopes of hydrogen, so deuterium, for example. It's still hydrogen, of course, because it has 1 proton in the nucleus. So it's still hydrogen, but these isotopes of hydrogen are showing that we can add these neutrons to the nucleus. So if the mass number is here, the mass number is 1 because we just have 1 proton present in this isotope of hydrogen. This mass number is 2 because we have 1 proton and 1 neutron, and they each weigh 1 atomic mass unit. This atomic mass here is 3. We have 1 proton still, of course, because we're dealing with hydrogen, just an isotope of hydrogen. And now we have 3 subatomic particles present in the nucleus, 1 proton, 2 neutrons. That's an atomic mass or mass number of 3. This is written out explicitly here as well. Know that some isotopes exist more naturally than others. They're more naturally occurring. This is the form we see of hydrogen most naturally abundantly. But there are these other isotopes of hydrogen that can exist. And again, we can tell these are isotopes of hydrogen because they are now with additional neutrons in the nucleus. What about this example now? We can identify the element based on its atomic number and the element symbol here for uranium. This atomic number tells us we have 92 protons. The mass number or atomic mass or atomic weight or that symbol A then will change because now we're dealing with isotopes of uranium. A trick question here could be how many protons are in this isotope of uranium, but then how many protons are in this isotope of uranium? What do you say to this? Well, there's still 92 protons, of course, despite it being an isotope. That doesn't matter. The number of protons tells us what element we're dealing with. What can be asked, though, is how many neutrons are present in this isotope versus this isotope. To figure that out, we take the mass number here, so 235 or 238. We know there's 92 protons, and we know electrons are essentially negligible as far as mass. So then we find the number of neutrons by subtracting the mass number by the atomic number. So some ways to think about this: the number of protons is the atomic number. The number of neutrons can be found by taking the mass number minus the atomic number, or the mass number minus the number of protons. Now, Dalton did some amazing things here, but I told you we'd come back to this one because part of this is proven wrong. All atoms of a given element do not always have the same mass. Why is this disproven? Well, everything we just talked about as far as isotopes. Isotopes of the same element will have different masses. Also, isotopes of the same element will also have slightly different chemical properties as well. The main part of Dalton's theory that's disproven here is that no, not all atoms of a given element have the same mass. We do have isotopes that exist. Here's a further written out explanation of that. Let's do this one practice problem now related to isotopes. So if we're asked how many protons and neutrons are in this atom, notice right away that we're not given the atomic number. We're only given the atomic mass here and the element symbol. This 153 is our uppercase A, the symbol for atomic mass or atomic weight or mass number. We know from what we just talked about that's going to equal the number of neutrons plus the number of protons. Well, how do we find the number of protons then if we're not given explicitly this atomic number here for europium? Well, we use this symbol for europium and we go to the periodic table. This version is available on Canvas, by the way. So we find europium, it is one of the lanthanides. We'll talk more about the organization of the periodic table in the next set of topics. Europium has this mass number ordinarily, so 151.594, or 151.964, excuse me. But here we have an isotope of europium. So this is about 152, but we're dealing with an isotope of a mass number of 153. The atomic number, or the number of protons, will still be the same for all isotopes of europium. That atomic number is 63. So far, we know the number of protons then has to be 63. The number of neutrons then, we are pretty close. We can take 153 minus 63. That means we have 90 neutrons in this isotope of europium. Chapter 2a, I'm going to break up into two parts. So in the next part of the expanded topics, I will talk about how we determine the number of electrons. For neutral atoms, to give you a sneak preview, the number of protons is going to equal the number of electrons, but this is not always the case. We have what's called ions that have either gained or lost an electron, and so again, we will come back to this concept. So I hope you're doing well, and I will talk to you next time. I'm also including here some animations that are copyrighted, and they are provided by the publisher. So feel free to watch these to get a little bit better of a visual on some of the experiments we talked about at the beginning.
A cathode ray tube is the forerunner of the television tube. It is a glass tube from which most of the air has been evacuated. When the two metal plates are connected to a high voltage source, the negatively charged plate, called the cathode, emits an invisible ray. The cathode ray is drawn to the positively charged plate, called the anode, where it passes through a hole and continues traveling to the other end of the tube. When the ray strikes the specially coated surface, the cathode ray produces a strong fluorescence, or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction. In 1897, J.J. Thomson, an English physicist, determined the charge-to-mass ratio of an electron. He adjusted the electric field so that the electrostatic deflection, theta E, was the same as the magnetic deflection, theta B, and was able to calculate the charge-to-mass ratio of an electron using the following equation, where E is the applied electric field, theta is the angle of deflection, B is the applied magnetic field, and L is the distance traveled by the cathode rays. Thomson determined the charge-to-mass ratio of an electron to be negative 1.76 times 10 to the 8th coulombs per gram. In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass. Radioactive elements can spontaneously emit three different types of radiation: alpha particles, beta particles, and gamma rays. Carbon-14 spontaneously emits beta particles from its nuclei. Since beta particles are attracted to the positive plate of an applied electric field, they must be negatively charged. In fact, beta particles are electrons that are formed and then emitted from the nuclei of certain radioactive isotopes. In the decay process, a neutron is converted to a proton and a beta particle. Cobalt-60 is used for radiation therapy and treating certain cancers. It spontaneously emits gamma rays from its nuclei. Since gamma rays are undeflected by an applied electrical field, they have no electrical charge. Gamma rays are very high-energy electromagnetic radiation. They have no detectable charge or mass. Radon-222 is being formed continuously in our environment by decay of uranium-238. Radon, being a noble gas, is chemically unreactive. Therefore, it is not trapped by chemical processes in the soil or water and is free to seep up from the ground and into homes. Radon spontaneously emits alpha particles from its nuclei. Since alpha particles are attracted to the negative plate of an applied electrical field, they must be positively charged. In fact, an alpha particle is composed of 2 protons and 2 neutrons. It is equivalent to a helium-4 nucleus. Both alpha and beta particles are deflected by an applied electrical field, while gamma rays are unaffected. Also note that alpha particles are deflected less by the applied electrical field compared to beta particles due to their higher mass. An alpha particle, composed of 2 protons and 2 neutrons, is approximately 7,000 times the mass of a beta particle.
The nucleus of an atom was first discovered when a beam of positively charged particles emitted from a radioactive source was aimed at a fluorescent screen. The particles caused the fluorescent screen to glow. When a very thin sheet of gold foil was placed in the pathway of the particle beam, a few particles were deflected to the side. Occasionally, particles were deflected straight back. But nearly all particles passed right through the gold foil, as if it were not there. The scientists concluded that atoms must be mostly empty space, and that because some particles are deflected, there must be a small positively charged central mass, which they called the nucleus.
In the early 1900s, J. Thomson proposed that an atom was a uniform sphere of positively charged matter in which electrons were embedded. This model is sometimes called the plum pudding model. Electrons are embedded in a sphere of positive matter, similar to raisins in plum pudding. In 1910, Ernest Rutherford, Hans Geiger, and Ernest Marsden carried out experiments in which very thin foils of metal were used as targets for alpha particles emitted from a radioactive source. Click on what Rutherford expected to observe, the results Rutherford expected based on Thomson's model of the atom. Based on Thomson's model, Rutherford expected that the positively charged alpha particles should pass through the uniform sphere of positively charged matter with little or no deflection. Click on actual experimental results to see what actually happens. Rutherford observed that the majority of alpha particles penetrated the foil either undeflected or with only a slight deflection. Every now and then, however, an alpha particle was scattered or deflected at a large angle. In some instances, an alpha particle actually bounced back in the direction from which it had come. This was a most surprising finding, for in Thomson's model, the positive charge of the atom was so diffuse, or spread out, that the positive alpha particles were expected to pass through the foil with very little deflection. Upon making this discovery, Rutherford exclaimed, "It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you." Click on Rutherford's model to see the model of the atom that Rutherford proposed based on his experimental observations. Based on the results of his experiment, Rutherford postulated a nuclear atom. All of the positive charge and most of the mass of the atom is concentrated in a very small volume called the nucleus. Electrons occupy the remaining space of the atom. The radius of an atom is approximately 20,000 times larger than the radius of the nucleus. Most of the positively charged alpha particles pass straight through the diffuse electron clouds of the atoms. Some alpha particles pass close to the small positive nuclei and are deflected at large angles. A few particles score a direct hit on the nuclei and come almost straight back.